Yeah. All right. Can you hear me at the back? Yeah. No?
I think that's alive. It's just not.
Okay. Well, it's my honor and a privilege to introduce a very, very distinguished computer scientist and inventor. And he's going to be talking on quantum computing, and which is going on at IBM. And Dr. Robert M. Szabo, Bob, a senior technical staff member and a member of the IBM Systems University Alliances team. Bob works closely with the worldwide IBM technical and sales communities. Oh my God.
I don't need this.
Our sales communities to create business results. Bob has over 30 years of experience in the field of computer science. He has worked for 7 years in the process control industry, designing process control systems and configuration tools. He has led design projects in the distribution, transportation, education, healthcare, and life sciences. He is a master inventor at IBM. He holds 27 patents, US and China. Today he is focusing on creating alliances with industry and university partners in support of the IBM system development and IBM Globe sales team. So let's welcome.
Okay, good afternoon, everyone. So I'm here today to give you an introduction about what IBM is doing with quantum computing. A lot of people may not be aware just how much we've done, and hopefully by the end of the talk today, some of you, maybe all of you, will be motivated to investigate quantum computing because you can do this all on your own for free. So let's move on. So what's the motivation for quantum computing? Well, kind of started real serious here in 1981. IBM and MIT hosted a physics computation conference, and I know the picture's a little bit fuzzy, but I don't know. The one face I can reliably pick out is Richard Feynman. Is up there, so hopefully you all know who Richard Feynman is, famous physicist. And during this conference, Feynman was said that he's not happy with all the analysis that go with just classical computing theory, because nature isn't classical, and if you want to make a simulation in nature, you better make it quantum mechanical. So this was kind of the start. Let's see. So some examples here. Why we need quantum computing? What's our motivation for doing all this research and trying to bring quantum computing to the market? It's impossible to model caffeine on today's most powerful high-performance supercomputer, which I believe today is the IBM computer at Oak Ridge National Lab. We could represent the structure of the caffeine molecule with 160 so-called quantum bits. Okay, so what does this mean? If we look at other representative molecules here, water, ethanol, acetaminophen, or Tylenol. There's caffeine there in the middle, sugar, penicillin molecule. You see that the number of bits that it takes is enormous. Okay, water's doable, but much beyond that, the numbers just get huge. To represent the molecular state with a qubit, and we'll talk in a little bit what a qubit is. We only need 14 for water. We could do caffeine with 160. Okay, I don't throw these numbers out just for jollies. I mean, the largest quantum computer IBM has announced is we have a 50 qubit machine, in the lab, not generally available yet for researchers, but we have one that's 20. So as quantum computers get bigger, we hope to represent larger molecules in their energy states.
So why use so many bits to represent these molecules?
The energy states between each electron, and they have to be represented as complex numbers. Okay. By the way, as you heard in the introduction, my background is computer science. I'm not a quantum physicist or quantum anything. I'll do my best to answer all your questions, but there's a lot I know I'm not going to be able to answer. So, what are some of the possible areas for quantum computing? Okay, so if you agree nature's quantum mechanical and classical computers are going to have a problem representing basic molecules, there's a need for quantum computing. What are some of the application areas? Okay, well, all this stuff has to be proven out yet, but based on what we know today, chemistry is an area that we think quantum computing is going to have some value, especially in things like material design, oil and gas, and drug discovery. Okay? Artificial intelligence, doing classification, machine learning, linear algebra, quantum computing we think has a role there. And in financial services, things like asset pricing, risk analysis, rare event simulation, we think this is another area. Okay, so next slide. IBM likes to use the word quantum advantage. Some companies use the word quantum superiority. We like to use the word quantum advantage. Let me explain this timeline a little bit. We see there, this is easier for me to see because it's bigger. Our first step on this road was laying the foundations for quantum. Okay? It goes back to almost the beginning of the 1900s when Albert Einstein did his work on the photoelectric effect and got a Nobel Prize for that. So from that point forward, through the early, mid-late 1900s, the fundamentals for quantum information science were laid. People started creating and scaling qubits with increasing coherence, more on that later. Creating error detection and mitigation schemes. Now, all this foundation work has been going on. I've got a timeline, I think, on the next chart that'll spell it out a little clearer. We're at the quantum-ready state today. Okay, we have people who've developed core algorithms, continue to do so. People have been working on increasing quantum volume. I'll explain what quantum volume is with the chart shortly. People are standardizing benchmarks, and we have a system infrastructure and enabling software. Okay. We launched something in the year 2016 called the IBM Q Experience, which I'll talk about near the end. And you see the red line, that's where we're at today. So sometime between now and the next 2 or more years, we hope to enter this quantum advantage phase, where we hope to demonstrate the advantage of using a quantum computer for a real problem of interest. Said another way, IBM is a business, extract commercial value. And then with that, hopefully we can enable new scientific discoveries because we'll be able to solve problems that heretofore we could only dream about solving on a computer. So a little basics. I'll try to keep this short. What's the difference between a bit and a qubit? Okay, so we all here should know that the bit's the basic unit of information that we know and love today. 2 possible states, 0 and 1. You look at a memory bit, it's going to be 0, it's going to be 1. And if it's 0 now and nothing overwrites it, come back tomorrow, it'll still be 0. A qubit is the basic quantum unit of information in a quantum computer, and it's also a 0 or 1 when you measure it or observe it. Okay, so this is where the quantum weirdness gets really difficult to follow, but it turns out it's really true. The difference between a qubit and a bit is that the state of a qubit can be a superposition or a combination of both 0 and 1. And there in the red, we kind of showed that some complex number A probability of the 0 state plus some complex number B probability of being in the 1 state. So if you look at this sphere here, they call that a block sphere. You see the z-axis pointing up arbitrarily. If the qubit is in that state, it's a 0. If it's straight down, it's a 1. And if it's on the equator, where the x-axis is, or the y-axis, it's 0.50, 0.51. Okay. This, by the way, here in the bottom corner, these are actual qubits here, these little squares. Let's see. Okay. So where does the power of quantum computing come from? Well, with classical computer, the potential power doubles every time you double the number of transistors. So if you can double the number of transistors, you've effectively doubled the power of the computer. And over there on the bottom left, you see a Power 9 24-core chip. That's our latest server chip. Over on the right, for a quantum computer, the potential power of a quantum computer doubles every time you add a qubit. Okay. What you see there is the IBM 16-qubit device, and the thing circled is one of the qubits. Okay. So with the quantum computer, we have exponential growth kind of working in our favor here. So if you have 1 qubit, that 1 qubit can represent 2 basis states. Some probability of 0 and some probability of 1. Again, the 2 probabilities are complex numbers. Remember that those vectors are on the sphere, and if you start rotating them, you can have an angle. All right. So 1 qubit, 2 states. So 2 qubits, you can have 4 basis states. A times the 0, 0 state plus B times the 0, 1 state, so on. Again, where the constants A, B, C, D are all complex numbers. Okay, so for 2 qubits, you have 4 basis states. 3, 8, and then if you have n, you have 2 to the n basis states. So it doesn't take many qubits to start getting into some really, really big numbers. Yeah?
But that assumes also that the qubits are entangled.
Yes.
Okay.
Yep. We'll I think I might have a chart that talks about entanglement. The IBM has announced a 50 qubit machine, so that machine can represent 2 to the 50 basis states. It's that number there in the red.
So how many of these are entangled?
I don't know anything about the 50, so I can't tell you.
Okay, so
the smaller machines, we know that answer because the qubit interconnects are actually diagrammed. In some cases, it's as high as, I think, 4.
Okay, so you shouldn't say 2 to 50, right?
I'm saying it.
But they're not entangled.
I didn't say that. I didn't say that either. Okay. I told you I don't know the specifics of the 50 qubit machine. I've never seen it. I don't have any access to that research. So please don't put words in my mouth.
Okay, I'm just trying to figure it out.
Okay. Okay. So 2 to the 50 basis states, big number. Okay. Let's see. Next. So in the picture, that's actually that is the quantum computer inside this Thing looks like an oil drum. It's called a dilution refrigerator. We'll talk more about that later. I got diagrams that show what's inside it. And you see it's on a raised floor. It's in a lab in Yorktown Heights. Let's see. Next page. Okay, so 275, if you had a 275 qubit machine, you have the potential to represent more basis states than there are atoms in the observable universe. Okay, so the potential here is great. Okay, a lot of work still has to be done. I was talking at the beginning to some of the faculty. 10, 11 years ago, we had 1 qubit. Today, we have 50. So we've come a long way in a relatively short time. Nobody knows where this is going to lead. So how do quantum computers work? Okay, so quantum computers leverage 2 quantum mechanical properties, one of superposition and one of entanglement, to create the states that scale exponentially like this. So what these charts try to show here is, in the left side, superposition. A single quantum bit can exist in some superposition between 0 and 1. Okay. Remember, straight up 1, straight down 0, and anywhere else some combination of the 2. Until you measure it. Once you measure it, it's going to give you one of 2 answers. It's going to give you 0, it's going to give you 1, but with different probabilities. If the vector were on the equator and you read it, you measured it 100 times, about 50 times you'd get 0, 50 times you'd get 1. Okay. N qubits allow for a superposition of all possible 2 to the n combinations. Then we have an entanglement. This is another feature where the states of entangled bits can't be described independently from each other. Okay? So if you entangle 2 bits, they kind of behave as 1. Again, until you measure it, until you look at it. Okay, the history timeline of quantum computing. So first thing I'll point out before anybody thinks to ask, what do the blue dots mean? Okay, so the blue dots represent some type of IBM involvement in that event. Okay? Surprise, we picked blue. So there in 1981, we had that conference. I showed you the picture. Quantum information theory started in the 70s. IBM worked on quantum cryptography in 84. And quantum teleportation in 93. In 2001, we experimentally factored the number 15 using Shor's factoring algorithm, which was invented in 1994. The Transmon superconducting qubit was invented in 2007. That's the technology that IBM uses as the basis for qubits in our quantum computer. There are other ways to represent qubits. We and some other companies use this thing called the Transmon. The coherence time, the time that the qubit would stay in a superposition, from 2007 to 2012, we made some big improvements in increasing that coherence time. In 2015, we demonstrated some simple error correction codes. In 2016, we made quantum computing available on the IBM cloud. I'll talk more about that near the end. And last year, we launched a commercial universal quantum computing, which I'll talk more at the end.
So in terms of coherence time, what's the scale you use now?
Microseconds. I have a chart that shows some of these parameters and error rates on the qubits. Okay, so 2 principles of quantum information science. Okay. Again, with the classical system, the states are reliably distinguishable. It's going to be 0, it's going to be 1. with the quantum system, attempting to observe the state in general is going to disturb the quantum device, and it's only going to get you partial information about the state. This is part of the uncertainty principle. Two systems can exist in an entangled state and cause them to behave in ways that can't be explained by supposing each particle has its own state. So this little picture here shows two qubits connected. So these can be put into an entangled state. This is the information I don't have on the 50. I've never seen it, but I'll show you a chart that shows these interconnects on the machines that you can access. We have a 5, I think a 14, and a 16, and a 20 qubit machine. Okay. Okay, there's several kinds of quantum computing. The so-called goal, I think, of most companies researching quantum computing is the so-called universal fault-tolerant quantum computer. Okay? This will allow you to run a useful quantum algorithm. It will allow you to achieve these exponential speed-ups over a classical counterpart. However, this is one of the problems. The overhead of quantum error correction, 1 to 5 million qubits. That's a very daunting task. We don't know how to do that. Today, we're doing what's called the proximate quantum computer, NISQ, noisy intermediate scale quantum. It's a quantum device that does not have fault tolerance. So our computers are noisy. They don't have fault tolerance. But they work well enough that you can demonstrate useful applications by interacting with the classical computing system and doing problems in quantum chemistry and optimization. That's doable on a noisy system like we have today. And we think 1,000 to 5,000 qubits would be enough to do something meaningful. Perhaps show even some kind of advantage or get us closer. Okay? That's a more tractable problem given today. Now there's this other thing that's some people will call analog, quantum-inspired, quantum annealer. These are specially built systems which may use quantum effects to solve or emulate a very specific problem. The programmability is limited, and nobody really knows if quantum computers that use this type of quantum technology are going to speed things up faster than a conventional computer. I mention this because if you've seen anything on the internet about quantum computers out there, there is a company that says they have a quantum computer with hundreds of qubits. Well, it's not a universal computer. It's one of these quantum annealers. It's using quantum effects, but it's a different kind of technology. Over here. I mentioned quantum volume, demonstrating an increase in quantum volume. So the power of quantum computing is way more than just the number of qubits you have. Okay, as this chart tries to show, quantum volume depends on several factors. The number of physical qubits, of course, is important, but the connectivity between the qubits is important, which is what you were getting at. The types of hardware gates or operations that you can do on the qubit, that matters. Also matters is the errors and decoherence of the gates, right? You apply a gate to a quantum computer, isn't always going to work. When you measure it, the measurement may give you an error, okay? So you got to take into account all these errors and the number of parallel operations you can do. So such that when you look at this two-dimensional matrix, if you have an error rate that's high, let's say 0.01, and you go from a 5-qubit machine to a 500-qubit machine. You haven't done anything. That 500-qubit computer is no more powerful than the 5-qubit one, because the thing's going to decohere, whether it's 5 qubits or 500. If the decoherence time is short, they're all going to decohere in a short period of time. What's important is getting these error rates down. So if you have a 50-qubit machine like we have today in the lab, and we can slowly get the error rate lower, then you see the volume of the box get bigger. That becomes a more powerful computer. So a 50-qubit machine with 0.001 error rate is more powerful than a 500-qubit machine with a 0.01 error rate. So if you do research and you see advertisements about number of qubits and stuff, there's more to it than just the number of qubits. You have to look into these other aspects. The type of quantum computing, and if it's noisy intermediate scale like we're doing, then you got to start looking at things like error rates and yeah.
Can I ask a simple question? What is the quantum volume?
Well, the volume is the number of qubits versus the error rate. So lower the error rate, the more qubits, the greater the volume, the more powerful the quantum computer.
Powerful in terms of numbers.
Ability to solve more complex problems. Okay, because a gentleman here, I think it was you who asked early on, you can only do your quantum calculation as long as the qubits are in superposition. Once they decohere, and we go through a lot of trouble to try to make these things stay coherent for a long time. That's why we got them in these drums, magnetic filters, vibration. All this stuff can ruin it. So the longer the qubits can stay in a coherent state, can stay in superposition, can stay entangled, the more work they can do. And we can quantify how much time you have, because we do publish these parameters for each qubit in the machine. Okay.
The clock speed must come into play, right?
Clock speed in what context?
Like every register, every reading, every writing.
Well, think of them as you're applying. When you apply a gate, you're changing the state of the bit or bits.
Right, but they have to within the coherent
But you have to do it within an amount of time of the shortest coherence.
Right.
So if you got a 5-qubit machine and the one that's got the worst coherence time, you got to do all your gate applications and measurements before that time elapses.
Is there a limit on how fast the clock speed can be?
Yeah. Yeah. Okay. So how many qubits are required to see a quantum improvement or a quantum advantage? Well, first of all, that's what's inside the drum. And now you get to see the whole picture, because the first chart kind of had this stuff chopped off. That's where the qubits are. They're in this part here, all the way at the bottom. The rest is getting microwave signals down to the substrate that's instantiated the qubits, and then the measurements back up. Okay, so this is the reality. We have approximate quantum computers today. We think we can do problems that matter for quantum chemistry, some specific optimization problems, and even some machine learning problems. The number of qubits we think you're going to need to do one of these types of problems is anywhere from 100 to 1,000. We're at 50 today. We're getting close to that 100 number. We think sometime in the next 5 years we'll be in this range. So this isn't happening this week or next week, next year even, probably. There's still a lot of work to do. This is really, we're really at the very beginning. To do a more complex problem, like Shor's algorithm, remember Shor's algorithm is the quantum algorithm that can factor a number into 2 primes. and big linear algebra problems, okay? We think you're going to need a universal fault-tolerant quantum computer to do those kind of problems. And you're going to need more than 10 to the 8th, qubits to do that. Why? Because the number of qubits overhead you need to do the error correction, it's just enormous. But if we can do that, we stand a chance to solve some really big problems that you can't easily solve today, maybe that you can't even solve today. But we're looking at 10 or 15 years away. A lot of people worry about this particular one and its implication to encryption, but we got a long time to figure out encryption methods that are quantum proof, and there is a lot of research going on in that today, and there are some algorithms out there that people suspect are quantum proof. We'll probably have that all worked out by the next 10 or 15 years. Who knows? Nothing to worry about.
So what do you think are the major barriers these days about these sort of increasing the power?
Well, we need more qubits, right, first of all. We got to get the error rates down for both measurement, for both applying gates, and we got to get longer coherence times. Because if we do that, even with a modest number of qubits you saw on the quantum volume chart, we're getting more powerful. If somebody said, here's 1,000 qubits today, and the error rates aren't any better than we have today, we haven't really done anything. But then there's a lot of engineering problems that go along with this. At least the technology we use. Remember, I said this is where the qubits are, all the way at the end of that drum. It's like an oil drum. 50 today? How's that going to scale up to 1,000, let alone 1,000,000, all in that space? Or you're going to need a dilution refrigerator, even bigger. I have a chart coming up, but temperature here at the bottom is like 15 millikelvin. It's colder than outer space. Cosmic background radiation is, I think, 3-something Kelvin. 15 millikelvin. And that's still noisy in there, right?
What's the physical size of each qubit?
We've asked for junk samples, but we can't seem to get them. But the substrate's about that big.
One bit?
No, and they can fit, 16 on something this big. Yeah, pretty small. Most of the space is taken up by these cables. These are coax cables that bring the microwave signals to the qubits to change their state, and then to measure them, and then the measurements go back up. Yeah.
So do you see we're not going to get there until we discover some new materials?
Well, new materials. There's other. I mentioned earlier on. There's other ways to represent a qubit, right? There's a company that uses trapped ions. They make, I think, rubidium atoms really, really cold, and then they use lasers to manipulate them. In comparison to the transmon, they're pretty slow. And I don't know how you scale up a big laser gadget like that, so it's got that problem. But there's other techniques people are investigating. I've got to believe the discovery that's going to crack this probably hasn't even been made yet. People are still thinking about it, researching it.
So for me, these problems of computer science, I know there are physics and engineering.
Mm-hmm.
Some of these engineering problems need to be solved. So if you talk about particular algorithm design, I think there are a lot of sort of new algorithms that's coming out.
That's part of the challenge, is how do you take a classical algorithm that we know and love today, and then how do you map that to how a quantum bit works? Please don't ask me that. You can ask, but I don't know the answer. This is, again, all in active area research, and especially to the students that are here today. I mean, this is the very beginning. I have a chart coming up, but this is like the beginning of electronic digital computing back in the 40s. This is right at the beginning. Somebody's got to figure out all this stuff. Like back in the 40s, nobody knew what a compiler was, right?
Yeah. Is there, are there any special languages?
We have a software development toolkit that's open, and there is a language. It's called QASM. Looks a lot like C. We also have a graphical editor that you can use to program the qubits. I've got some pictures I'll show you. All freely available on our website, and I'll give you those websites here at the end. Okay, so we need a lot of good qubits, low errors before we can get to these things. You had a question, yeah.
Why we can't put many qubits in the same place at the bottom of the reader?
Why?
Is it causing a lot of heat?
Well, they have to all be very, very cold. Our qubits are based on Josephson junctions, which is a superconducting device, and it has to be near absolute zero. A little bit of heat, vibration, magnetic noise can all disturb the coherence time. And the quantum state only exists here. You can't put another box next to this, another drum, and expect those two environments to be the same. They're not.
So the major problem is the heat.
Well, heat's important only because we use these superconducting devices that have to be really, really cold. But I'm told by one of our physicists that even a stray electron migrating across the substrate can mess up the frequency at which one of these qubits operates. I shouldn't say mess up. It changes the frequency enough that you can actually measure it. Can you imagine that? An electron migrating through the substrate, and it throws off the frequency, and we can measure it. How do you stop that kind of noise? I don't know.
Because when you measure, you got to shoot something in and get a signal back. So
Right.
that's
And once you do the measurement, the quantum state collapses, and you get your 0 or your 1 with whatever probability, and then that information has to flow back up. Got to get amplified several times before it comes out the top.
where are most of the errors coming from now? Like where is the
Well, you have errors due to the coherence time.
Yeah.
Okay. You have errors due to doing measurements. You have errors due to applying the gates. Trying to get the qubit into whatever position you want it to be
So
in.
if they're working on entanglement distance. So if you were theoretically make that distance larger, then you would be able to have a higher probability of error rate going down.
I can't say that would follow. I don't understand it to that level where I could say that would follow. But what I can say is that the quantum state exists there in the drum, and everything quantum has to happen in there. And if you wanted to put 1,000 bits in there, you're going to need 1,000 coax cables coming down, 1,000 coming back. I don't know how you do that.
So the basic problem is in the estimation of the number of good qubits, right?
Yeah. And they're all different. I'm glad you said that. I mean, you might have 20 qubits there, and some stay coherent longer than the others. Some have better error rates. So, we compute and report an average. And I think the software toolkit also reports the errors per qubit. So you probably don't want to use the qubit with the worst coherence time unless you really, really need it.
So you're saying those qubits are like pounded into a state of like the weakest one is always going to be the weakest one.
That's going to govern the length of time you have. If you're going to use all the qubits on the device, that's going to govern the length of time you have to do your quantum.
Right, but I would just,
experiment.
every computation, is the weak one always gonna be the weak one, or it just
I-
changes?
I
with the
don't really
computations?
know the answer to that. I suspect the answer is yeah. I don't think that parameter changes much over time. I think the frequency can change, but its coherence, I think, is what it is. But IBM, we recalibrate these machines. It used to be twice a day. And again, let's go to the next chart because this shows some of the operating metrics that are available. So this shows the interconnects for the 20 qubit machine. We used to have 2 of them. I think we might only have 1 now. Doesn't matter. But that shows the interconnect. So let's look at these times. So we've got the frequency. Here we're just showing an average. I think if you go to the website and you use one of these machines, it'll tell you this information on each qubit. At least it used to. This stuff, massive development. This stuff's changing all the time. If you decide you're going to investigate, download the tools, you'll get friendly with GitHub and you'll be updating, frequently. So we got the operating frequency. The T1 time in microseconds tells you how long, if you take it from the low energy state 0 and put it into 1, that tells you how much time it's going to go back to 0 on its own. Okay. So in this case, the average is 90 microseconds. T2 is the time that the qubit will stay in a coherent state. So in this case, the average is 45.92 microseconds. So if you're going to do a quantum experiment on this device, it's got to all finish in 45 microseconds because microsecond 46, they all decohere and it's... Okay. So you got to apply all your gates, make your measurement before T2 expires. The errors when you apply a gate, if you put a qubit from the low energy state to somewhere on the equator, okay, that's a gate. That's an operation, gate operation. 10 times out of 1,000, it's going to mess up. Okay. A readout error or a measurement, if you measure a qubit 16 times out of 100, you're going to get a mistake. And if you do a multi-qubit gate, so if you've got some qubits entangled, and you apply a gate to the entangled qubits, those operations are going to mess up, 5 times out of 100, 6 times out of 100. Okay, so when you run a quantum experiment, you actually the toolkit has a parameter called shots, tells you how many times to run the experiment, and then it prints out a histogram and tells you, kind of lets you determine how many times you got 0, how many times you got 1, or how many times you got 0, 0, how many times you got 0, 1. I think I have a chart that kind of shows you that. So, and then again, these interconnects, they're different. The 5-qubit machine had limited number of interconnects. The 16's a little different. Here's the 20. I have no clue how they hooked up the 50. Okay, so I mentioned the quantum experience. This is the thing that we announced in 2016. Better pick it up here. We've got the quantum computer at IBM Research in Yorktown. We've got the IBM quantum bit device, the qubit device. These are the qubits, these squares. That's 1 qubit. Those squigglies are microwave resonators. They're part of the circuitry that lets you manipulate the qubit and to measure it. And here's the quantum experience. There we're showing the graphical editor. I have a better picture. But we've got this whole platform. It's available on the cloud. It's free. You can all sign up for an account. I expect all of you are going to run out right after the end and sign up. You can download this stuff. There's training material, there's tutorial material. the editor, the software toolkit, and more importantly, you can run these experiments on the real quantum machine. Okay, I'm not going to get your answer back like that because it goes into a queue. But you can actually run them on an actual machine. You can run them on a simulator, and no cost. And as far as I know, we're the only folks in the quantum realm doing everything, you know, soup to nuts, letting you have at it for free. I think I mentioned earlier on, we had some scientists model the low energy state of a lithium hydride molecule. They did that on the 5-qubit machine. Noisy as it is, error prone as it is, they actually did some useful work. So this is where we're at. Okay, in the 1940s, we had the first electronic digital programmable computer called Colossus. The British invented this thing, and nobody knew about it until the 1970s because they kept it secret that long. They used it to break German naval codes. This is the quantum computer today. Other than it being in color, I mean, kind of looks the same. What you see here in these racks, these are arbitrary wave generators. These are the things that generate the microwave pulses that manipulate the qubits and make the measurements. And depending on the AWG that you have, you might need one of these per qubit. You might need one per 4 qubits, depending on how many channels it has. These are very expensive, not to mention the cost of that dilution refrigerator that's getting the thing really cold. Takes up a lot of space. This is a lab device. This is why it's on the cloud. Okay?
It doesn't look like this.
Doesn't look, yeah, they got paper tape on that. Yeah. But this is very exciting. I mean, if I was 18 again, I'm not sure, you know, let's say a couple of years ago, I'm not sure I would have told an 18-year-old. I shouldn't say that to a bunch of computer science people. Yeah, it's studying computer science. So much has been commoditized. You know? When I got started, I mean, we were still 16-bit, 12-bit computers. Unix was just invented. Okay. Now with this quantum computing, I mean, this is a chance to begin right at the beginning of a whole new paradigm in computing, and you can learn. You don't have to, you know, be working for a secret government agency at a time of war to learn this stuff or to contribute. You can do it today from your, from your office, from your room. All you need is a laptop and an account on the Q Experience. Right at the start. It's very exciting time. So this is kind of what it looks like. It's a little cleaned up, but you see a couple of the machines are here. There's 1, 2. This is the control device that controls the refrigerator. These things are called dilution refrigerators. They use an isotope of helium 3 and 4, to do the supercooling. Very expensive machine, but you can, it's a commercial device. Okay, so here's what the inside looks like. So you already seen the racks with the microwave electronics, so we won't say any more about that. Here's another picture of the inside. It starts at about 40 Kelvin at the top, and by the time you get to the bottom, it's 15 millikelvin. This thing here, this little square here, is that, and the little black square in the middle, those are the qubits. And that is the black square there. You see, let's see if we can count. 1, 2, 3, 4, 5. Looks like 6, 7. Let's see. 2, 4, 6, 7 qubits. Again, the squiggles for the microwave circuitry. So this thing's protected from the environment, multiple shields. I mentioned magnetic shielding, you know, heat, vibration, you name it. And we use, I already mentioned this, we use the helium-3 and 4 isotope, which is what drives the cooling process. Okay. You may have noticed, I don't know if it shows up on this picture as well, but you see some of the cables, they all have little loops in it, and that kind of helps as things get cold. It gives the cables some slack, so as things start shrinking down, they don't pull apart. Just getting that stuff to work in those temperatures is, you know, it's a big deal. Okay, here's another kind of look at the same thing. Okay, takes about, I'm told, 3 days. If they turn it on a Friday, then Monday morning the thing will be cooled down, and then they'll leave it run for however long. If they have to do some kind of serious maintenance on it, then they'll shut it off, warm it up, and go to work. All right, so this Q Experience, since we announced it in 2016, we're actually over 100,000 users now. This is a little chart. We have people logged in with accounts on all 7 continents, so I guess when you're in Antarctica for the winter, what else is there to do? So we have at least one scientist down there. We've had 7 million or so experiments run by now. There have been 125 papers citing these resources. And we've got 1,500 colleges and universities worldwide, including 300 high schools. Okay. So here's one way to program the quantum computer. Each row represents a qubit in time, so time increases from left to right. Each qubit starts in the 0 state. Then you start applying these gates, these little blocks with letters. H is called a Hadamard gate. That gate will put a qubit in the superposition by putting the vector right on the equator, so 0.50, 0.51. You apply these gates left to right, and then you see the little purple thing looks like a speedometer. That's the measurement operator. And at the end of this experiment, they're going to measure qubit 1. And you'll notice you can save these programs. You log in, you get them back. You can run them on the real machine. You can simulate them on a simulator. The simulator acts as a perfect logical qubit device, whereas if you run it, you'll see the errors. That's why you got to again run the experiments multiple times to kind of see where the answer is tending to.
So your quantum programs are defined by the number of qubits, right?
Well, you have qubits, and then you have the program is actually defined by how you apply these gates,
The gate, okay.
right? And in this particular interface, I mean, if I'm reading the comment there on the description, this looks like they're implementing Grover's algorithm, which is a search algorithm. The programming is just done by drag and dropping the gates onto the screen. Okay. Okay, so we have this thing called Qiskit. This is an open source framework for quantum computing. you can get it for free. Quiz kit, let's see, this part of the diagram I can't see on an angle. Okay, so, so you've got the hardware, you've got the software on top of the hardware, and then we have these things, libraries. We have these a thing called Aqua, Terra. We have Terra and Aqua exist today. I don't know what Ignis and Air do, but those are the four old elements, right? You know, earth, wind, fire. I think in Latin. I have a chart here that talks about what Aqua and Terra do. Aqua gives you a library of quantum algorithms that you don't have to figure out, somebody's already figured out, so it's a library of algorithms. And you can use these on our noisy intermediate scale computer. We have enough in here where you can do chemistry experiments, AI experiments, and optimization experiments on the existing machines today. They even have translators, so if you've been doing quantum chemistry work on some classical tool that's well known out there, this thing can actually accept data input in the format that those classical tools use. Here's an example of the QASM language over here. Stuff runs on Python. Qiskit Terra. This lets you. This gives you a set of tools that in your quantum programs allow you to manipulate the pulses. And I can't explain this, but my understanding is that the shape, amplitude, phase, all this stuff of the microwave pulses that manipulate these bits, all that stuff can be modified. And again, another active area of research. So they've made controlling the circuit pulses and stuff available to researchers. You know, maybe there's a better way to do it than we're doing it today. Who knows? Okay. Okay, so commercializing, I think we're getting near the end here.
When you run the thing on the simulator, there's this is the classical computer behind it.
Yeah.
It will generate noise and errors.
No, the simulator's perfect.
I see.
Yeah, that's think of the simulator as built out of logical qubits. They're perfect. If you do an experiment that you expect to be 50-50, it'll be 50-50. You do that same experiment on the real computer, you might get 0.53 and 0.47. Okay, so in 2017, we announced we're building the first universal quantum computers for business and science. Just another look in the cleaned up lab. We've got this thing called IBM Q. It's the IBM Systems Group. That's where I'm part of. We've got IBM Research, and we've got IBM Global Services. So the research folks do what you expect. They advance the research in physics, math, computer science, so on and so forth. The systems team is working to create a secure, flexible, reliable infrastructure to run this stuff. And we have our business services folks who are working on strategy and getting industry and applying industry expertise, working with clients to look at how we might be able to use this stuff. The Q Network, kind of three goals here. Accelerate research. We can't do it all ourselves. That's why we're letting everyone have at it. We hope it's going to help launch commercial applications by engaging industry partners. And, you know, this is probably kind of the most important to you all in this room, is that it's going to help you get educated and prepare, you know, be part of the beginning. So when, you know, a big bank comes along and says they need a quantum programmer to work on their risk analysis for their portfolios, yeah, you'll have a job.
The Q Network has, we've got these kind of 5 categories. We have things called hubs.
You'll see a lot of these hubs are at universities. We've got, or national labs, okay? A hub has a relationship with IBM, has access to the biggest quantum computers that we presently have, which is 20 for public use. And each of these hub members are allowed to invite, I think, up to 3 partners that can work and access the quantum device through that university. So one of the more recent ones was North Carolina State, and I think the school in Germany, 2 of the most recent announcements. We have a school in Japan, Australia, England. We have partners made up of companies. These are real partners that we have working with us.
Banks, high-tech companies, auto companies,
Consulting companies. We have some academic partners. Universidad de Minho, that's in Portugal, MIT, you know, Massachusetts. We have members, some more industry partners here. And we even have relationships with startup companies. Okay? And the ones you see there listed. This is kind of interesting because KO University, I guess I said 3, well, apparently it's at least 4, because KO has 4 industry partners working through KO, doing their own quantum research and collaboration. KO on our computer. Okay. This stuff all costs money. This stuff isn't free anymore once you start this space here. This kind of graphically shows you how the partner structure, member structure, hub structure works. Okay. I can't say more than this. I spoke to the faculty. If at some point in time FIU becomes interested in things like academic partnerships or maybe even a hub, these discussions you know, we'll have to set up with our business development people. We've done under non-disclosure. And that's all I can say. So this was the North Carolina announcement, which happened in May of this year. So pretty recent. These are some of the benefits of, you know, joining the Q Network. There's technical support, of course, for the system use, access to educational content resources. There's a advisory council of reps from each organization that's joined. There's industry academic workshops, opportunities to share, and opportunities to exchange and collaborate across the network. So just because, you know, there's 2 separate universities, that doesn't mean, you know, they can't be collaborating with each other. The whole idea is to try and get as much collaboration going as we possibly can. So specifically, you know, a role for colleges and universities. As the university, access to the latest hardware, control software, software libraries. This is all the kind of stuff that you need to be able to do if you're going to, you know, carry on a, you know, a serious research program. And because you know, you're going to need a lot of money. You want to build your own quantum computer. I'm not saying you can't do that, and I'm not trying to discourage you from doing that, but maybe later. This is kind of an easy way to get started. Okay. This chart here shows the lithium hydride ground state energy. This is the thing that this guys were modeling on the 5-qubit machine. So I've already kind of said this, but these are the areas, the workloads that we think quantum computing is going to have a role in. And we've already demonstrated some of its ability to solve problems in chemistry. Admittedly, pretty small molecules, but the fact that they did it again with the 5-qubit machine, pretty impressive. They actually published an article, I think, in Nature last year that describes this research. Okay, so the future, there's the future. The quantum machine, maybe they'll look like this once everything gets all prettied and cleaned up. This last page here, these are the key URLs that you might want to remember. And if you don't want to remember, if you're still interested, just search IBM Q Network and you'll find all this stuff. First link talks about our initiative. We have the Q Experience that lets you start using the machine, using the graphical editor. QuizKit.org, that's the website to get the software development kit. I think you can also download with that. You get these Jupyter notebooks, which, again, are there to teach you all about stuff. And then this last one here, if you're interested at some point in the future becoming an IBM Q Network member, we've got information about that on the web as well. Okay. But the first three things are there for free for everybody, students, faculty alike. And I encourage you to, if you're interested, have a look. I think that's it. I ran a little late. I'm sorry. I hope it was worth it. Thank you for your attention.
So how do we start? If we would like to teach a course on Q computing here for students, what is the first step that you would like you to do with your idea?
Well, if I was sitting out there as a faculty member, and it's me, since 8 months ago I didn't know anything about, 8 in November, and about 12 months ago I didn't know anything about this stuff. I download the quiz kit and start learning this stuff. Okay. After 12 months, do I feel I could teach a course in this? Probably not, but this isn't my full-time job either. I mean, I haven't exclusively studied quantum computing for 12 months. I don't want you to think that. But I would start there at the quiz kit. I'd get the simulator, get the Jupyter notebooks, get all that training stuff. We even have a game. It works on your phone. Hello Quantum. It shows you a couple qubits and gives you a state of the bits that you got to get yourself into by applying gates. So it starts kind of helping you think about how qubits operate and how gates operate. IBM Hello Quantum works on Apple and Android. But I think that's where I would start. Now, if you knew all this stuff, and you probably would still start at the quiz kit, and you could start trying to put a curriculum together. I don't know if we have any curriculums available. I know MIT does. MIT has on their online course website a Q curriculum. I guess now that I mentioned that, I guess if I was going to be a teacher next year, I'd probably take that course from MIT. Again, not knowing too much about the stuff, that'd be a good place to start. Because to do a small class, I mean, everybody in the class signs up, gets an account, and you can run experiments. You can run them on your laptop using the simulator. Okay. Any other questions, comments? Okay. Thank you.